Well, welcome to the 2018 BC only FRQs. So we're not doing the AB ones. You're doing those on AB, and you can find those videos on the AB YouTube page. So for question number 2, this was one that actually kids really struggled with, mostly because of parts B and C. But question number 2, researchers on a boat are investigating plankton cells in a sea. At a depth of 8 meters, the density of plankton cells, it's kind of interesting, in millions of cells per cubic meter is modeled by P of H is equal to, and then the expression. Now that's only going to be valid when H is between 0 and 30. There's a different function called F of H for heights of greater than or equal to 30 meters. F is not a function that we've actually been given explicitly, so we don't know the equation for F. Part A, we want to find P prime of 25, and then we want to interpret what that means. Well, this is a calculator active problem, and so we can find that by using our calculator. I already took the liberty of defining P. I'm just going to do a quick double check, make sure I typed it correctly, which I do recommend if they give you a function on one of these FRQs that you take the time to define it. You're probably going to use it multiple times, and then you also take the time to double check it. Now I want to specifically find this at 25, this derivative of 25. So there isn't a way to do that. Menu, option 4 calculus, option 2 derivative at a point. Our variable we're using is H, and we're going to evaluate this specifically at 25, and this will be taking the derivative of P of X. And I get negative 1.179. I could take that out further if I wanted to, but there's no reason to. So I have negative I'm going to actually write this out. So P prime of 25 is negative 1.179. And I need to interpret this. Now remember, P is the density of the cells. And now we've done a rate of change of that specifically at 25. So this, at an H at a height of 25 meters, P prime of 25 is the rate of change. Or you could say, is the rate of change of the density. That's fine. You still have to do the units, which I'll do in a minute. Or you could say, I'll phrase it a little bit differently, at H of 25 meters, the density is decreasing. That's another language for rate of change. Now I'm saying decreasing because that derivative was negative. At a rate, somewhere you should be using that word rate, okay? So whether it's rate of change or decreasing at a rate of, and then I'm just going to rename that rate, and I have to do the units. Now, P was at millions of cells per cubic meter. And we just did a rate of change of that. So I'm going to add in the per again. And this was with respect to H. Okay, H was our input, and H is in meters. So if people struggle with that because of the units in particular and the interpretation. All right, part B. We have a vertical column of water. Okay, so we've got this vertical column of water. And each cross section in here has an area of 3 square meters. That doesn't make it actually a square. I don't know. It's a column. It's probably more circular. But that area is 3 square meters, 3 meters squared. We want to find out how many plankton cells are in this column of water. Well, this is a situation where we know the cross section. We know the cross section, but we do need to also be careful about what they're asking for. They want how many plankton cells are in this column. They're not asking for what's the volume of this column. They want how many plankton cells are in this column. So we're kind of merging the idea of volume here with a known cross section, but converting this to plankton cells. So when we do volume of known cross sections, we would do a definite integral of the area of one of the cross sections. Well, in this particular situation, we don't want though just the volume. If they just asked for the volume, this would be fine. And students, what students did is they knew that that's how you would do that, and they did this. If they had said, what is the volume of the water, that would have been the correct way to do this. But that's not what they asked for. They asked for how many plankton cells are in this water. Well, plankton cells can be found by multiplying the density times how many millions of, or by the cubic meters. Let me show you why. The volume would be meters cubed. And then the density is millions of cells. Oops, didn't mean to do that. Per cubic meter. If you multiply those together, watch what happens. You're left with the number of cells. That's really what we're looking for. So I'm not just doing the area. I'm going to do the area times the density so that I can basically convert out this volume to millions of cells. Well, density, remember, was P of H. And that really surprised students. There's always at least one question on the FRQ where kids go, I'm not really sure what happened. This year was the plankton problem really caused problems for our BC students. They had a really hard time on this one. So let's give this a shot. So I'm going to be doing the definite integral from 0 to 30 of 3, which is the area of the known cross-section, but I have to multiply this by the actual density because we're wanting to find the number of cells, not just the volume. And this is, again, I've already defined P, so I'm saving myself some time here. I get 1,675.415-ish. So this is part B. So this is approximately 1,675.415. And they said to the nearest meter. If they tell you that, you have to round. So I'm going to round this to the nearest meter, which is 1,675. And this is to the nearest million. They're kind of giving you your units. This is how many millions of cells we have for part B. Part C. There is some other function called U. It's greater than or equal to F, and it's always positive, as is F. You might go, what is F again? F is the density of the cells if the height is greater than or equal to 30. And this is going to be true. H is going to be greater than or equal to F for all heights that are greater either equal to 30. And what we know is that the definite integral from 0 to 30 of this unknown function U is 105. The column of water in part B is K meters deep. Let's assume that K is bigger than 30. In part B, the height was exactly 30. Now we know it's bigger than 30. We want to write an expression involving one or more integrals. This is a hint. You're probably going to need more than one. That's a hint. That gives the number of plankton cells. That's the same as what we did before in millions for the entire column. The column is now bigger than 30. And explain why this must be less than or equal to 200 million. Well, we already know that we have a way to model the number of cells for the first 30 meters. This is from part B. I need a way to model the cells, the number or the density or the number of plankton cells for heights higher than 30. Well, starting at 30, and I don't know actually how tall the height of the column is. I just know that K is what that height is being represented by. And then this would still be, there's still known cross sections of 3 for the entire length of the column. But now we can't use H anymore or P anymore to talk about the density. They said that once we start getting to heights higher than 30, the density is actually F. We have no information for F. But what I do know is that H is greater than or equal to F. So I'm going to use H instead. I'm sorry, not H, U. Because I know that it's the closest thing I've got. I would rather overestimate a little bit than underestimate. So from here, oh no, actually I will write F, I just don't know how to evaluate it. So this is the actual density, or the actual number of cells in millions. But now they want me to show, why do I know that this has to be less than or equal to 200 or 2,000 million? Well, I actually know what this is. We calculated this. Now, I'm not going to use that rounded answer. I'm going to go ahead and use the more accurate answer. And then this one, I don't actually know what f of h is, so I can't really evaluate that. But what I could do is I could evaluate this at u. I could evaluate this at u because remember, f of h is less than or equal to u of h. So if I'm using a little overestimate, if I could show that a bigger value is still less than that 2,000 million, then something smaller than that or equal to that would also be less than that 2,000 million. So I do actually know what u of h is when I integrate it. They told us that the integral from 0 or from 30 to infinity of u of h is, let me fix that, is 105. Well, if it's 105, then I would be able to use something even less than. Okay, so this is an overestimate. And I could even take that to infinity here if I wanted. I know that that which is something that is bigger than f is this definite integral without the 3 is 105. If I multiply that by 105, I end up with 1,990.415 million of cells, which is definitely less than the 2,000 million. And the 1,990.415 is an overestimate, since f of h is less than or equal to u of h. And we did this to an infinite height. Thus, if we actually use the real values, it would have to be less than 2,000 because an overestimate was less than 2,000. So thus the real amount must be less than 2,000 million as well. All right, part D. The boat is moving on the surface of the sea. At a positive time of t is greater than or equal to 0, positive or non-negative, I should say. The position of the boat is x of t, y of t. And then they've given us the derivative of x and the derivative of y. Time is measured in hours, t hours. X of t and y of t are meters. Find the total distance traveled by the boat over the time interval. Now, some students right here, start wanting to use the total distance formula. A lot of times this is wrong, but a lot of times people are trying to use this. Okay, you can't use that with the parametric. And so you can only use this if we're moving in one direction, like along the x-axis or along the y-axis. That's an A-B type of concept. This one, we're changing both x and y. This is arc length. Arc length is the total distance traveled. So we're going to use the arc length formula, which is the definite integral from 0 to 1 of the square root of the derivative of x with respect to t quantity squared plus the derivative of y with respect to t quantity squared dt. So this is what I'm going to now use the calculator for. Now, they already gave me the derivatives. I don't need to take a derivative again. I just need to make sure that in my integral I write it properly and I do my square rooting as well. All right, so this is a definite integral from 0 to 1 of the square root. And I did not put in these yet because they're only going to be used once. So I already know what x prime of t is, but I'm going to need to square that. So I'm going to include some additional parentheses. So I have 662 times the sine of 5t. I'm going to get out of the parentheses for the argument and out of the parentheses for that entire derivative so I can square that derivative. Plus, and I'm going to introduce new parentheses because I'll be squaring the derivative of y, 880 times the cosine of 6t and I want to make sure and square that entire expression. And then this is all with respect to t. So I get 757.456. Now, what are we measuring? This is a word problem, so I should think about units. This is the distance traveled by the boat, and they told us that was in meters. All right, the next question that was a BC question for 2018 was question number 5. This one is non-calculator active. So we have the graphs of polar curves r equals 4. Okay, so that's a circle with a radius 4. That's this one. And r equals 3 plus 2 cosine of theta. That's this one. Are shown in the figure above. That's that limacone with a dimple. The curves intersect at theta equals pi over 3. And also at theta equals 5 pi over 3. And that was nice that they told you that, because you guys know that is not always fun to solve for those. R is the shaded region that is inside the graph of the circle r equals 4 and outside of the limacone with dimple r equals 3 plus 2 cosine theta as shown above. We want to write an integral expression for the area of r. By the way, there's multiple different ways that you could do this. The way I chose to do it is I chose to do 2 times the top area. You could have done twice the bottom. You could have just done the whole region from pi over 3 to 5 pi over 3. That's up to you. You might remember that the formula for the area in between polar curves is 1/2 times the definite integral. Now, if I'm doing the top, I'm going to do from pi over 3 to pi. I'm just doing this region right here, and that's stopping at pi. And then I want to do the big radius squared minus the small radius squared. Remember, the big radius is the outer boundary. So that would be 4. I need to square that radius. And then the smaller radius squared would be 3 plus 2 cosine of theta, quantity squared, and then d theta. This is different than the answer that they put on the scoring guideline, but it is correct. All right. We only had to write it. We didn't actually have to evaluate it. Yay. Part B, we want to find the slope of the tangent line to the graph r equals 3 plus 2 cosine of theta at theta equals pi over 2. We have a formula for the slope of a tangent line for polars, but often students don't remember it. And it's not hard to derive, so sometimes students will derive it right in the middle of the problem. I'll do it that way just in case people have forgotten the formula. You might remember that y is r times the sine of theta, and x is r times the cosine of theta. So if I want to do dy over dx, I would do the derivative of y with respect to theta. So the first times the derivative of the second plus the second times the derivative of the first. And since this derivative is respect to theta, not r, I have to do times dr over d theta. On the denominator, I'll do the first times the derivative of the second plus the second times the derivative of the first. This formula is sometimes written in a different order. That's okay. Now, what we know is that we want this to specifically be evaluated when theta is pi over 2. I'm just going to take a moment and evaluate a couple of these things so I can substitute in a little bit easier. Remember, r is 3 plus 2 cosine theta. So r evaluated at pi over 2 would be 3 plus 2 times 0, or 3. So everywhere here for r, I'll be able to plug in just a 3. dr over d theta, if I take the derivative of r, let's see, cosine's derivative is negative sine, so this would be negative 2 sine theta. If I evaluate that specifically when theta is equal to pi over 2, as they've asked us to, this would be negative 2 times 1, or negative 2. All right, so if I now do my entire derivative evaluated when theta is pi over 2, I already know that r at pi over 2 is 3. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. And dr over d theta at pi over 2 is negative 2. For my denominator, I'll pull that negative out front. I have negative, and then r is 3. The sine of pi over 2 is 1. The cosine of pi over 2 is 0. I don't really need to keep going. on that, but here we go. So on the numerator, I end up with -2. On the denominator, I end up with -3. And so my slope here is 2/3. Part C, a particle moves along the portion of the curve. For the limacon, r equals 3 plus 2 cosine of theta from 0 to pi over 2. So we're starting here and we're moving to here, essentially. Let's see. The particle moves such a way that the distance between the particle and the origin, what is this? The distance between the particle and the origin? That's r. That's the radius. Remember, these are all formed by radii that are changing. R increases at a constant rate. They're telling us the rate of change of r with respect to time because it's 3 units per second. This is going to be a related rates problem. Find the rate at which the angle theta changes with respect to time at the instance when the position of the particle is at corresponds to theta is pi over 3 and indicate units of measure. Well, we are talking about how r is changing, so we should start with the equation for r. And I'm going to do a derivative of this implicitly with respect to time. Well, that'll zero out. Derivative of cosine is negative sine, so this is -2 sine of theta times d theta over dt. We're doing this with respect to time. Now I'm going to substitute in, and theta is pi over 3. So when theta is pi over 3, then the sine is √3 over 2. And I will now solve for d theta over dt. These divide out. So I'll get 3 over -√3. You can choose to rationalize that or not. I am going to put in units here. I think this does rationalize out to like -√3 if you wanted to. Indicate units of measure. Okay, they told us indicate units of measure. So I want to make sure and do this. So we're doing the rate of change of theta. When we do our units of measure, this tells us the order to do it. So we're doing, so this is -3 over √3, or you can rationalize it. Well, theta, any angle, is measured in radians per time, which is measured in this problem in seconds. So there's our units of measurement. I didn't score the last couple problems, so let's go back and do this. We'll start with number 5. All right. Our integral does look different than theirs, but it is the same. But you might as well see how they scored it, the constant and the limits. Now we have a different constant out front and different limits, but they are equivalent. So we would get that first point, and then we do have the correct integrand. So we have 2 points for that. All right, part B. Having the equation for the derivative of y with respect to theta and x with respect to theta is going to get you 1 point. Even if you didn't realize, even if you didn't do them both correctly, you just need one of those. And then the second point comes from dy over dx. Now, what if you jumped right to dy over dx? It's fine. They could look at that and tell that you did the derivative of y with respect to theta or x with respect to theta correctly. So if you actually started here, you get both the first and the second point, and then the answer is 2/3, which we got. All right. And then here's kind of another way where they just do some of the evaluating at a little bit different pace, or kind of just do it a little bit differently, but it's the same thing. Part C, they want us to, let's see. They did this one just a little bit differently than I did. I started more with the formula for R. They did some dimensional analysis to show that dr over dt could be found by doing dr over d theta times d theta over dt. That shouldn't be a concern at all because we did do that. If we go back and we look, we did it numerically instead of with the expressions. But we did right here end up dividing all of that and multiplying that all together. So you can see that that is still here. We just did it with the expression instead of keeping it in terms of the functional notation. So we did do that. So we did get that point. Let's see. I'm on this one. Oh, I'm not. There we go. So we did it, but we did it differently. And then same thing here with number 1. We kind of did this all numerically instead of with all of the abstractness of the dimensional analysis. And we did have the correct answer. Ours just wasn't rationalized, radians per second. So we would get all 3 of those points. All right, we did not yet grade question 2, so let's do that. This was the correct answer that we got. And at a depth of 25, you do have to specify because derivatives are at an instant, so make sure you do that. The density is changing at the rate of. I put decreasing at the rate of. That's fine. Now, when I put decreasing at a rate, I didn't put the negative. Oh, I did put the negative. Okay, I would have missed this actually. If I use the word decreasing, I can't use that negative. If it's decreasing at a negative rate, it's really increasing. So this would need to be decreasing with a positive here, or I could put changing at a rate of and kept the negative, which some students prefer to do that because then they don't do what I just did and miss that problem. So I would have missed the problem for the meaning. And then millions of cells per cubic meter per meter. So I only got 1 out of 2. Part B, the integrand. Basically, that's this part right here. So knowing that you had to do 3 times the density, which was really tricky, very few kids got this at all. Very few students got any points on part B. Very few got any points on part C as well. And so we have, all right, we have an integral expression. That's correct. Compares the improper integral. We did it verbally. They are doing it in writing. I think theirs is probably more powerful than the way that I did it. And then an explanation to show that it would have to be less than that. So I do believe that our explanation by saying that was an overestimation going to infinity is fine, but I think theirs is probably a little bit better. But I think we would have still gotten those points. I was only an AB grader on the year that this one came out, so I'm not 100% sure it's possible we would have gotten 2 out of 3. I suspect we would have gotten 3 out of 3. All right, part D, the integrand. We have that correct, and we have the correct total distance with units. It didn't actually say here that we had to not have the units. They might not mark you down with the units because it didn't specifically say that you had to have the units there. All right, let's go back to the last question on this year's FRQs for BC. The Maclaurin series for the natural log of 1 plus x is given by, and then we have the Taylor series, or the Maclaurin series below. On its interval of convergence, it converges to the natural log of 1 plus x. Okay, that's what convergence means. It means that when you write that polynomial, it's a match for what that original expression that we can't usually talk about in an algebraic form would be. So those transcendental functions. F is going to be called some other function. Notice that this is a manipulation of the original expression. We want to write the Maclaurin series for F, the first 4 non-zero terms, and we also want to write the general term. Now, some people do this all in one step. I'm going to split this into 2 different steps just because it's what my brain can handle a little bit. Remember that we already know what the original expression would be. Now, they didn't name it. I'm going to call this g of x for this Maclaurin series that they gave us at the beginning. For me, I rely heavily on functional notation as a guide for me. Not everybody does it the way that I do it. Some people are able to process things a little bit faster than I am, so you may not feel the need to do all of these steps that I'm going to do. But f of x would be changing slightly. The 2 things that change is we have this multiplier in front, and since it's a monomial, we can do that. And also it changes the input here. Instead of just an x, we now have x over 3. So this would be x times g of x over 3. These are the 2 things we're going to change. We're going to multiply each of these terms by an additional x, and we are also going to change the input. So the first term, I'm just going to write it like this. There's your first term, your second term, the third term. We want the first 4 terms, and the general. And then let's see, I'll be changing my input, which is why I'm writing these empty parentheses. All right, so for each of these, I'm going to be multiplying all of these by another x as one of my manipulation techniques, including my general term. Put that wherever you want. And I'll be changing the input to x over 3. I'm going to simplify this a bit, and what I'd end up with is x squared over 3 minus, let's see, this would be an x squared times another x, so x the cubed, and this would be 3 squared, which is 9 divided by 2, which is 18, or you could write it like this. Sometimes I write it like that because sometimes it helps me with the general term. It's up to you. Then I'd have x to the third times x, and then I have 3 times 3 to the third. You could simplify that if you want, but it might not help. I have x to the fourth times x, and then 4 times 3 to the third. And again, writing it like this for me helps me see the pattern better. I can see the terms are still alternating. Now, you might wonder why this is n plus 1 instead of n. That's because if we plug in, it looks like these are starting with n is equal to maybe 1. Then I would end up with a positive number here because I'd have an even power. All right, and then all of these have x. Now this was x to the n times another x, which would be x to the n plus 1. I can kind of use that general term to manipulate. On the denominator I have this n, and I also have this 3 to the n, which I'm just going to move to the denominator. Oops, with a pen. And if I check and compare, as long as n is 1, to start off for this one, that would work. Now, if you changed it to n being 0, you would have a different general term here, and that's fine. It'll still be graded and evaluated, so they would look and see if yours is different, if it would work if n is 0. Part B. Determine the interval of convergence for the Maclaurin series for f. Show the work that leads to your answer. I'm going to be using the ratio test with that general term. All right, so this is the limit as n approaches infinity of the absolute value of, I'm going to start with the general term, but I'm going to add 1 here. I'm going to add 1 here to this general term. So this is to n plus 1. So instead of n plus 1, this would be n plus 1 plus 1, or n plus 2, if you would. And then remember, this was x to the power, oh, let's see, and I'm finding this, let me make sure I'm finding for the right one. This is for f. So I'm using this general term right here. So x to the power of 1 more than n plus 1, so n plus 1 plus 1. And then instead of n, I have n plus 1, and then times 3 to the power of n plus 1. I'm going to divide this by the original general term by multiplying by its reciprocal. And then all of this is supposed to be less than 1 in order for this to converge. So from here, my absolute value tells me that these alternating signs of -1 now become insignificant. So I'm going to totally disregard those. And I'm going to do some simplifying here. Well, the n and the n plus 1 do not simplify down. Since there's that plus 1, you cannot reduce those. Don't try. The 3 to the n and the 3 to the n plus 1 would reduce to 3. The x to the n plus 2 divided by x to the n plus 1, if you subtract those powers, would be x to the power of 1, and this is less than 1. Because this is a limit for n, I'll pull out x as an absolute value, and then this is the limit as n approaches infinity of the absolute value of n over, if you want, you can distribute 3n plus 3. Now, we're doing this as a limit to infinity, so we're looking at the ratio here. These have the same coefficients, so the ratio of the coefficients is 1/3. So the absolute value of x times 1/3 is less than 1. And so x would be between, the absolute value of x is less than 3, and x would be between 3 and -3. But I do need to check the endpoints. This is not a geometric series, so I'm going to look at the endpoints here. Let's look first when x is equal to -3, and I'm going to rewrite this general term and replace it with a -3. looks like for all of these, and started at 1, we had decided a little while ago. Okay, so I have negative 1 to the power of n plus 1 times negative 3 to the power of n plus 1 over n times 3 to the power of n. Well, I can rewrite this a little bit because I can think of this negative 3 to the power of n plus 1 as negative 1 to the power of n plus 1 times 3 to the power of n plus 1. That's really what that is. Well, so this 3 to the power of n plus 1 is going to reduce down with 3 to the power of n really nicely. So what I'll end up with is the summation as n goes from 1 to infinity. The negative 1 here times the n plus 1 times the negative 1 here, well, it's going to be squared times itself. So when you square that, you would get just a 1. So it no longer alternates. And then this 3 to the n plus 1 over this 3 to the n would just be a 3. So this is 3 over n. Well, we could think of this as just 3 times that harmonic series. So this is the harmonic series, and it diverges. Because it's just multiplied by a constant. So I will be using an open interval here for the negative 3. When x is equal to positive 3, again, I'll use that same original expression as n goes from 1 to infinity of my general term. This would just this time be 3 to the power of n plus 1 over n times 3 to the power of n. Well, if I rewrite this alternating part stays, and I just have times 3 over n. So this is an alternating series. Okay, so we have an alternating series. This would be 3 over n for the terms. Those are going to decrease in magnitude. And the limit as n approaches infinity of 3 over n is indeed 0. So this one converges by the alternating series test. Yes, you need to say the name of the test. Yes, you need to list the condition. Do not just say converges. You need to list the conditions. That's why I listed harmonic series. By the way, sometimes people will say they compare it to the harmonic series and then multiply it by 3 and say since it's greater that it also diverges. You can use the direct comparison test there. But if you pull that 3 out front, that's indicative of it just being a constant multiplier, and you're fine. So because it converges at 3 but diverges at negative 3, our final answer here would have that inequality for its compound inequality. That was tough. Lots going on there. All right, part C. P sub 4 of x is the 4th degree Taylor polynomial for f. Okay, so we're still working with f, our new one. About x equals 0. Use the alternating series bound to show that p sub 4 of 2 minus, to find the upper bound. In other words, they're asking us to find the error. We're not finding the interval. We're finding the max error. That's what they mean by upper bound for this. This is the error. Okay, so if they want the 4th degree, that would be up to here. Okay, so the error is basically what the absolute value of p sub 4 of 2 minus f of 2 would be. Okay, that error is going to be less than or equal to the absolute value of the next term. So the next term, since we did a 4th degree, would be the 5th term. So it would be the absolute value of negative x to the 5th over 4 times 3 to the 3rd, and specifically at x is equal to 2. So that error would be less than or equal to, and I'm going to do the absolute value here, right? So 2 to the 5th, which is 32, over 4 times 3 squared. Now I'm going to leave it like that. If you wanted to evaluate it, you could evaluate it if you wanted to. Let's just check the scoring guideline here. All right, the first 4 terms, they're giving us 1 point for that. I'm just doing a quick double check. And it looks like ours are the same, so we've got that point. If I compare it to the general term, ours is the same. So we've got those 2 points. All right, Number 5, the fact that we set up a ratio gives us a point. The fact that we compute the limit of the ratio gives us another point. That we found the correct radius gives us a point. That we even consider both endpoints, even if we do them wrong, gives us a 4th point. So even if you like really butchered the endpoints, you've got 4 out of 5. The analysis and the interval will give us the last point. There's an alternative method down here that I'll let you look at your own kind of leisure. Now the analysis part right here is important. So these are just the 2 ways to do the radius. So we've got this. They did a direct comparison to the harmonic. We multiplied out front and just said it was a multiplier, but that was fine. We rewrote this, used the alternating series test, and we had the correct final. So we got all 5 of those points. I would say many people are going to get maybe 3 or 4 of those points. Alternating series bound. The upper value of the error is the magnitude, meaning the absolute value of the next term. So we use the 5th degree term to find the max error. And then the answer, which we did not bother to simplify, but that is equivalent. So we got all of those. And that is the end of this video. Thank you very much.